Our final team has developed a small-scale wind turbine that will be of interest to residential home and business owners. Using wind energy, homeowners will be able to reduce their power bills by using the electricity converted from wind. Please allow me to introduce our last team, the vertical axis wind turbine.
Hello, good afternoon. We are the Vertical Axis Wind Turbine Group. My name is Clara Hoffmeister. I'm a mechanical engineer with Materials Option.
My name is Jigme Dukpa, Mechanical Engineering, Energy Systems.
Hi, my name is Alex Colon. I'm the aerospace major on this project.
My name is Tarun Thampi. I'm the mechanical engineer with Mechanical Systems Option.
Okay. Some of the benefits of using a wind turbine is to supplement the energy that's already existent in your homes. Vertical axis wind turbines specifically can be used in a more urban environment because they use turbulent flow in order to work. This will be beneficial to supplement the energy and reduce your energy bills. Some of the benefits are that there is no pollution caused by using this turbine. You can use a battery, but it's not necessary for normal use. You can directly plug it into your already existing grid. There's zero carbon emission, and the noise is actually fairly low for these turbines. You can use it in your residence or small business. They're easy to install and fairly easy to maintain since all of the electrical equipment is actually located on the ground.
When it comes to actual vertical turbines, there are two basic schools of thought. There's your drag and your lift. Your drag is like you would picture a weather vane or an anemometer. It's got cups, and one is facing the wind and one is against the wind, and the difference in drag causes it to spin. A lift one is a little bit more complicated. The easiest way to think of it is if you think of a plane just stuck in a constant turn. It's got a lift pointing at a tangential angle, and it just spins around a center point. The drag are inherently self-starting. That means at pretty much low to no wind speeds, they'll be able to start up, whereas the lift always has to draw from some external energy source. That means they have to have either a battery backup or they have to pull from the grid before they can even start producing energy. The major upside to the lift is that they're able to capture a lot more energy at higher wind speeds. So if you were approaching, say, gale force winds, you definitely want to lift over a drag.
This is our hybrid design. It combines both the drag mode and the lift mode benefits. The turbine starts in drag mode, where as you can see the blades are parallel to the spires. This allows the turbine to create drag and be inherently self-starting. Eventually, after the turbine reaches a certain speed, the blades will turn and become at a 90-degree angle, and the turbine will be in a lift mode. This transformation mechanism happens because the blades are pinned. It is 100% mechanical and wind-powered. It doesn't require any kind of additional computer or any electrical power that'll rob from the system. The expected output, based on size and calculations, is approximately 1 kilowatt, which will amount to up to 3,500 kilowatt hours per year. This is based on assuming a 40% operation time. In total, it weighs under 200 pounds.
Assuming the industry standard of 10 to 40% operational time in wind capture with at rated power of 1 kilowatt, the annual output of our wind turbine is about 3,500 kilowatt hours. This meets about 10% of an individual's annual electric consumption currently in Florida. What the same individual pays about $1,600, according to the Energy Information Agency, pays about $1,600 annually for his electric consumption. Of that $1,600, we save him about $400 with our turbine. The turbine's initial cost is about $3,500, with overall maintenance over a period of 12 years or so is about $1,500. So the overall cost you're investing in is about $5,000. This cost is offset though by government rebates and production tax credits and things like that. Yeah, and the turbine takes about 12 years to recover the cost that you put in for it.
Some acknowledgements. I'd like to thank Progress Energy for providing majority of our funding, Dr. Juago, our technical advisor, for providing a lot of supplemental funding, and research assistants Jeremy Lawrence and James McKee for showing us how the various processes we use to create these blades work. and of course, Paul Hofmeister for a lot of additional advice, and our machinists, Mike Simonuk, who machined a lot of the mechanical components, and Luminatech, who was responsible for water jetting our foam.